So in the final segment of this lecture, I want to talk about how we estimate these Q and T parameters in IBM Model 2. And in particular, we're going to focus on something called the EM algorithm for estimation of parameters in these models. So here is a definition of the parameter estimation problem. As input to the parameter estimation algorithm, we assume a set of sentence pairs. So I'm going to use EK-FK to refer to our kth training example. And that example consists of an English sentence. So this, for example, could be the dog. And this is a French sentence, which is assumed to be a translation of the English sentence. Here's another example. So we might, for example, find that our 100th training example consists of this English sentence together with this French sentence. As output from the model, we want parameters of the form TFE or QIJLM. So, for example, we might have an estimate of T of le given there, or we might have an estimate of Q of 1 given 1, 6, 7. This, remember, is a distortion or alignment parameter. Now, a key challenge in this problem is that we are assuming that we do not have alignments on our training examples. Okay, so in an ideal situation, somebody would have annotated these alignments. So these alignments would have been present in our training examples. But that's really a unrealistic assumption. It's an extremely laborious task to annotate these alignments. And, typical training set sizes can easily be, in the order of hundreds of thousands of sentences. We might have 500,000 sentences of training data. And it's just too much to expect humans to annotate all of these alignments on all of our training examples, or really for any significant subset of our training examples. So that's going to be the key challenge. And that is going to mean that we need to use something called the EM algorithm, which is really a rather remarkable algorithm. This can be used for estimation in this kind of scenario where part of the data is hidden or missing. These alignments are unobserved. So let's, as a warm-up for the EM algorithm, first consider the case where the alignments are observed. Okay, so let's just for now assume we're in this idealized setting where we do actually have training examples with alignments. So each training example would now be a triple, EFA. For example, this might be a 100th training example, specifying an English sentence, a French sentence, and an alignment between these two sentences. So this particular alignment would say that the first word in French is aligned to word 2, second word is aligned to word 3, and so on and so on. Okay. So as I said, each training example is a triple, EFA. We're now assuming we have alignments. So in this case, deriving maximum likelihood parameter estimates is basically trivial, and it looks very much like the other parameter estimates we've seen earlier in this course. The ML estimates are just ratios of counts taken from our training data. So, for example, if I want to estimate the probability of le given there, I just set this as the ratio of two terms. So on the numerator is the number of times that these two words have been aligned to each other, are seen aligned to each other in the training data. And on the denominator, I have just the number of times I see the English word. So that's a particular example of this definition. So again, numerator, number of times I've seen E aligned to F. Denominator, number of times I've seen E. Similarly, the maximum likelihood estimates for the distortion parameters are a simple ratio of counts. This numerator count is the number of times I've seen word I in French aligned to word J in English, given that the two sentence lengths are L and M respectively, and the denominator is basically the number of times I've seen the ith position aligned to anything, given that we have the lengths L and M of these two sentences. So that's the warm-up. This is the case where the alignments are observed. I'm actually going to now write some pseudocode to be absolutely explicit about how these counts are calculated. The main reason for this, though, is that we'll see that the EM algorithm
is in some sense, well, it's certainly very closely related to the pseudocode I'm about to show you, to the algorithm I'm going to show you. There's just a couple of twists.